All right, we're gonna do another example here. And we haven't really used the perpendicular direction of 10 so far, so this example will take advantage of the perpendicular direction here. I'm gonna kind of describe what you have going on. You have, when I was a kid, we used to play a game called tetherball. It's like you had this, it was on the playground, you had like this pole and you had a string and you had like a kind of a volleyball sized ball attached to it. And the object of the game was to get it to wrap around the pole. So you'd hit it and then somebody else would try. It wasn't really a safe game. You'd hit it, and somebody would be going against you, try to hit the ball the other way, and the first person to get to wrap around the pole would win. And so we're gonna do an example. If you don't know what tetherball is, you can picture like that's a yo-yo and a string, and what you're doing is you're just gonna whirl it kind of in this circle. So I kind of dashed out the path of the mass at the end of the string here, so it goes through here, and it kind of looks like, I don't know, like an ellipse or something like that. It's just a circle that we're kind of giving some perspective there. And let's just call this angle theta, that you're kind of whirling it in a circle. This is your vertical right here. This is the string attached to a mass, and you're just kind of whirling it in a, a horizontal circle there. Okay, so given this situation right here, let's call this mass M. Let's call that theta right there. Let's solve for AC, centripetal acceleration. I'm not going to tell you a lot of things. I'll tell them to you as we go kind of here. So we're given the situation right here. We have a mass, we have a theta, some velocity v. Let's say it's going some kind of vt. They don't tell you what it is. They say it's just going some, they might say constant speed, be around the arc right here. And keep in mind, you can have a centripetal acceleration because as this ball goes around the circle, it's constantly changing direction. So every time it wants to fly off tangent, there's a centripetal acceleration pointing back toward the center. Okay, so, and one thing to consider here, we have the force of a rope, and we haven't talked about ropes in a while. If you see a rope and you talk about forces, you got to start thinking about tension. Okay, so step one, draw your picture. Step two, we're gonna label our forces, and sometimes what they'll do on the AP test, they'll give you a dot, and they'll say, hey, here's this dot, right, like this. And they'll say, on that dot right there, and that dot could be the ball right there. They'll say, on this dot, label the forces. So maybe let's get in a good habit of saying, if they gave us a dot, could we label the forces that are acting on our mass right there? So if you wanna pause the video and label your forces, then come back, see if you get them right. So hit pause right now. All right, we're back. So if we're the ball right here, automatically you're on planet Earth. If you want to get a force right on the AP test, you have force gravity. A lot of people get in the habit they draw down force gravity, and then they automatically draw down the normal force. And don't feel bad. It's a common thing because people kind of go on autopilot, but don't go on autopilot because ask yourself, the only reason you have a normal force is because you're making contact with something. So maybe the ball was on a table or a block was on a ramp, and there was a gravity force bringing it down to the ramp, but then normal force is pushing back. Well, on this ball right here, gravity is definitely pulling down, but it's not touching a table, it's touching a rope. So you have to ask yourself, what force do we have in a rope? We have the force of tension, and it's pulling up and to the left, just like that, okay? And I kind of drew the whole rope there. Here, let's just call it, I'm gonna make it a little bit shorter. Boom, let's call it FT. FT. Just like that. Okay, so those are the forces acting on our object right there. You get good points just for drawing them right there. And we are eventually going to have to break that force tension into X and Y components. Actually, not X and Y components, R and perpendicular components. Oh wait, the fun's going to start in about a minute here. So step one, we drew a picture. Step two, we label all our forces. Step three, we're going to show our coordinate system. If you want to go back to your original drawing, you can. Let's keep our FBD. Let's leave it alone. On the AP test, if they say label your FBD, don't start messing it up with all these different things. They want to know that you can label an FBD. So we'll go back to this original drawing and say, okay, we know we have the gravitational force Fg pulling down. We know we have Ft going just like this. But we have to show how we're going to label our coordinate system. And we always say, identify the center of your circle. Boom, right there. And unlike the roller coaster example, it was like a vertical circle. This is a horizontal circle, so keep that in mind. We're going to label our coordinate system toward the center is positive, and then perpendicular is going to be up and down. It's always helpful to know if you're dealing with a vertical circle or a horizontal circle because you got to find the center and then line up your radial direction with that right there. So step one, drew a picture. Step two, labeled our forces. Step three, pick our coordinate system. And I just did the little dot here because sometimes they will make you label your forces in the dot. And if they ever say label your whole forces, not the components, seriously, just label the whole forces because they'll actually, I've heard rumors they take off points if you start putting components on the dot, but so I've never seen it happen. So picture forces, coordinate system. Now step four, we're gonna sum our forces. Give them one equations. So let's do the radial direction first. That's always kind of fun. In the radial direction, we look right here, we're like, okay, in the radial direction, we have tension point up and to the left. In the radial direction, we have to pick out the part of that tension force that's actually pulling left right there. So if you want to kind of picture this, I'm going to take this triangle right here, and we had this tension force like this. Tension's going like that. And this is theta right there. And then you're like, oh, oops, I forgot my T. Don't forget your T. The tension force is pulling left and it's pulling up. Those are the individual components that make up the overall tension vector right there. And if we're talking about the radial direction, we have to pick out the component of tension that lines up with our radial axis right there. And if you look, that's going to be this part. So we have to go back and do a little trig. So here's our angle theta, here's our FT, and we want to find out what FT in the radial direction is going to be. We want FT in the radial direction because we're talking about the radial direction. We have our theta, we have the opposite side of the triangle, and we have our hypotenuse. So SOHCAHTOA, what goes with opposite and hypotenuse? It's going to be sine. So I'm just going to do a little work here. I'm going to say the sine of theta equals FTR. That's the part that's lined up with the radial direction, because we care about in the radial direction, over hypotenuse, which is FT. In the radial direction, we want to pick out just the FTR. So I'm just going to say, I need you FTR to pick you out sometimes, my FT over FT. If you want force tension in the radial direction, it's just your FT times the sine. So that's what I'm going to put right here. FT times the sine of theta. And I know it bothers some people. They're like, oh, I thought sine always goes with the y and cosine goes with x. Well, first off, we're not dealing with y's and x's. We're dealing with perpendicular and radial direction. But just do the trigonometry right there. You realize, oh, it's the opposite hypotenuse I care about. Okay? And there is no other force acting inward. So we set this equal to MAC. And that should make you happy because we're looking for AC. That's what the question wanted. So we have that. But, you know, we don't know tension. We don't, the mass, they gave us mass M. So we're going to look at the perpendicular direction and see if we can simplify some stuff down. Okay, so you do the perpendicular. That is a really bad sigma. Do better sigma than that. I'm not going to cross it off. But in the perpendicular direction, we look at this right here. We're like, okay, the perpendicular direction, that's up and it's down. We definitely have gravity. And according to our perpendicular direction right here, gravity is going to be negative because upward is positive. If you really want to think about like the old school y direction, you can do that and it wouldn't be wrong necessarily. You get it right. So FG negative plus, we have to get, we don't care about that tension, that's the overall, or this tension. We care about this tension right here because remember it's pulling over and up. We have to pick out the up part of the tension right there. So I could say plus force tension in the perpendicular. We have to pick that out and we'll do that in a second here. And in the up and down direction, in the up and down, it's not rising or falling, so your net force is going to be equal to 0 newtons. Keep in mind, the radial direction most every single time is going to be equal to MAC because along the radial direction, it keeps changing direction, so it'll have an acceleration. Let's talk about this real quick. FT in the perpendicular direction, that's this part right here, FT in the perpendicular direction. So we want to pick out the adjacent side of the triangle, and we have the hypotenuse of the triangle as well. You could probably use a tan if you wanted to too, but I'm going to involve the FT because I know I have an FT right there. I want to get this, so I'll say cosine of theta equals the adjacent, which is FT in the perpendicular, over hypotenuse. I'm picking that one because I want to get the FT involved because I have an FT in my other equation. I'm like, okay, so the cosine of theta is FT perpendicular divided by FT. I'm looking for FT perpendicular, so I times that over, times it over here. Force tension in the perpendicular direction is FT cosine of theta, which is exactly what you would think it would be because you're trying to pick out that side of the triangle, right? So I'm just going to simplify this a little bit. And don't forget, fug equals mug. And so I'm going to do a little simplification here. I'm going to plug in mug right there. I'm just going to add it over that side. So I find out FT cosine of theta equals mg. And that kind of makes total sense. Like even if you're not a math wizard, you're like, I'm not digging this at all. You can picture a force gravity has to be balanced off by some force going upward, and it's the FT perpendicular component right there. It's, if we zoom into that triangle, it's that part of the triangle right there that's balancing out the gravity force, which is exactly what your math says right there. So we have two equations. Something sweet's gonna happen. Just trying to get you ready for it. We have two equations, and I just want to see if I can get it simplified down at all. We're looking for AC. We have FT, and they didn't tell us anything about FT, so I mean, they just call it FT. So one little thing we could do, we could solve this equation for FT and then sub it into that one to get the FT out of there. So let's just for fun. This FT, we're going to solve equation 2 for FT, then plug it into equation 1. So if I do my math correctly, FT equals mg over cosine of theta. And I'm going to take blue. It's my favorite G2. My dad actually got these for me. the blue ones. I didn't have a blue one all year. You might have noticed that in my videos they were lacking. And so all I'm gonna do is just say, hey, I solved equation 2 here using the perpendicular direction, and I solved for ft, and I'm gonna plug it in right there for the ft in our first equation. So when I do that, actually, boom, I'm gonna do my work right here. So check this out. Instead of ft, I'm gonna have mg over the cosine of theta times sine of theta equals MAC. And whoa, whoa, whoa. I don't know this is a trigonometry class. I see sine over cosine. That makes tangent. MAC. And then I have M on this side, M on that side. By. And you get G tan of theta equals the centripetal acceleration. So something kind of cool about your centripetal acceleration. It does not depend on mass. It just depends on the planet you're on, gravity, and the angle you're making. So that is your centripetal acceleration equation. For this could be a mass in a string in a horizontal circle. It could be a yo-yo. It could be lots of different things, just a mass attached to a string. I hope that helps. That's kind of a more complex example because we drew our picture, we labeled our forces, but then this force in particular, we had to break into radial and perpendicular components using a little trig, and that's the next step kind of stuff there, okay? You do have one of those in your homework. You will have a chance to practice that though. But we just did the same process, picture, forces. We showed our coordinate system, boom, right there. And then we just summed our forces in the radial direction and the perpendicular direction. And then we just did a little substitution to get the tension out of there, just because they didn't really tell us much about the tension. And a nice simple equation that just depends on gravity and the angle. And one other thing, I know we've talked about radians a lot in circular motion. Radians can be helpful. But let's say they said, oh, this is 30 degrees. 30 degrees, you could take the tangent of 30 times 9.81, and you would get a centripetal acceleration of 5.66 meters per second squared. So like if you're like, hey, say they actually did give you an angle, and it was in degrees, you could do that. You could say tan of 30 gets that times 9.81, and I am in mode. I'm in degree mode. So you can be in degrees sometimes, like if they gave you the question in degrees, totally legit to do that. Your final answer would be meters per second squared. But yeah, in general, you leave it in variables, but if they happen to give you like, oh, the angle's 30 degrees, well, the tan of 30 is about 0.58. 0.58 times 9.81 is about 5.66 meters per second squared. So they could give you numbers and you could plug them in if you wanted to, but you know, the more we do physics, the more just do everything in letters anyway. So very cool. Thank you for watching. And if that one's a tough example, don't stress out because we'll have many more chances to practice with tough ones like that. Yeah, it still follows our 5 steps for success. Picture, forces, coordinate system, sum your forces, and solve. Thanks for watching.